December 16th, 1944. Ardennes Forest, Eastern Belgium, 5 o'clock in the morning. Colonel George Axelson, commander of the 406th Artillery Group, stood in his command post, listening to reports that were arriving from forward. Observation posts about German artillery fire that had begun, pounding American positions along what had been one of the quietest sectors of the entire Western Front. The barrage had started precisely at 5:30. Hundreds of German guns firing simultaneously across an 80-mile front, shells falling on American positions that had been thinly held because commanders believed this densely forested region was unsuitable for major offensive operations and because veteran divisions had been pulled out for rest after brutal fighting elsewhere. Axelson had been in his position for less than 2 weeks, having taken command of an artillery group that supported the 106th Infantry Division, a newly arrived unit composed largely of soldiers fresh from training who'd never experienced combat. The initial reports suggested a local attack, perhaps a spoiling operation or a probe to test American defenses. But as dawn broke and the scope of the German assault became clear, Axelson faced a decision that would require using a weapon system so secret that its employment had been forbidden on European soil until this moment for fear that enemy forces might capture intact examples and reverse engineer the technology. His artillery batteries were equipped with shells fitted with proximity fuses, designated VT for variable time, but called POSIT in communications to disguise their nature, devices that had been used against Japanese aircraft in the Pacific since 1943 and against German V-1 flying bombs attacking England and Antwerp, but never against ground targets where capture was possible. The standing orders from Supreme Headquarters Allied Expeditionary Force were explicit. VT fuses were authorized only for anti-aircraft fire over friendly territory, where falling duds couldn't be recovered by enemy forces, and artillery commanders were to continue using conventional time and contact fuses for fire missions against ground targets regardless of the tactical situation. But the German offensive that was unfolding that morning was threatening to overrun American positions, was pushing through defensive lines with armored spearheads supported by infantry that were advancing faster than American forces could establish coherent resistance, and Axelson understood that the conventional artillery fire his batteries could deliver might not be sufficient to stop attacks that were being pressed with intensity that suggested this was no local operation, but rather a major offensive that could replicate the German breakthrough in 1940, when Wehrmacht forces had crashed through these same forests and defeated French and British armies in 6 weeks. The story of how proximity fuses came to be available for use during the Battle of the Bulge begins not with the German offensive, but with a technological development program that had been initiated in 1940 when the United States, still technically neutral, but increasingly concerned about the wars consuming Europe and Asia, had mobilized scientific resources to develop weapons that could give American forces advantages that might prove decisive if the nation entered the conflict. The National Defense Research Committee, established in June 1940 under the leadership of Vannevar Bush, represented an unprecedented collaboration between American universities and the government, bringing together the nation's most talented physicists and engineers to work on military problems that required solutions beyond what existing military research facilities could provide. One of the most pressing problems facing anti-aircraft defense was the challenge of detonating shells close enough to aircraft to destroy them, a problem that had plagued military forces since aircraft had first become significant factors in warfare. Conventional anti-aircraft shells used time fuses that required gunners to estimate range and aircraft speed and then set fuses to detonate after a calculated delay, a process that introduced multiple opportunities for error and that produced hit rates so low that thousands of shells might be fired to achieve a single kill against maneuvering aircraft. British forces defending against German air attacks during the Battle of Britain in 1940 had fired approximately 20,000 anti-aircraft shells for each German aircraft destroyed, a ratio that indicated just how ineffective conventional anti-aircraft fire was against modern aircraft. The solution that American scientists proposed seemed almost like science fiction, a shell that could sense when it was near a target and detonate automatically without requiring any timing mechanism or gunner calculations, a proximity fuse that would transform anti-aircraft fire from a game of chance into a reliable weapon that could protect ships and cities from air attack. The development of the proximity fuse was assigned to Section T of the Office of Scientific Research and Development, a research group established at Johns Hopkins University Applied Physics Laboratory under the direction of Merle Tuve, a physicist who'd worked on radar development and who understood the electronics and physics necessary to create a device that could fit inside an artillery shell and survive the tremendous forces of being fired from a gun. The technical challenges were enormous, requiring the miniaturization of radio components to fit within the cramped space of a shell nose, requiring these components to survive accelerations of 20,000 times the force of gravity when the shell was fired, requiring a power source that could activate instantly and provide electricity for the few seconds the shell was in flight, requiring all of this to be manufactured at scale by industries that had no experience building such sophisticated electronics. Tuve assembled a team that grew to over 200 scientists and engineers, bringing together physicists who understood radio wave propagation and electrical engineers who could design circuits and military ordnance experts who understood what artillery shells experienced during firing and flight. The basic principle was elegant. A miniature radio transmitter in the shell's nose would broadcast signals that would reflect off nearby objects, and a receiver would detect these reflections and trigger the detonation mechanism when the reflected signal strength indicated the shell was close to a target. The execution was brutally difficult, requiring the development of vacuum tubes small enough and rugged enough to survive being fired from a gun, requiring circuits that could distinguish between reflections from intended targets and reflections from the ground or clouds or rain, requiring manufacturing processes that could produce these sophisticated devices in quantities measured in millions, rather than the dozens or hundreds that scientific instruments typically required. By 1942, after 2 years of intensive development and thousands of test firings, Section T had produced a proximity fuse that worked reliably, that could be manufactured in quantity, that transformed anti-aircraft effectiveness in ways that would prove decisive in campaigns from the Pacific to Europe. The first combat use of proximity fuses came in January 1943, when the cruiser USS Helena engaged Japanese aircraft during the Solomons campaign, using 5-inch anti-aircraft shells fitted with the new fuses and achieving hit rates that stunned observers who'd become accustomed to the futility of conventional anti-aircraft fire. The Helena's gunners reported that shells seemed to track aircraft automatically, detonating precisely when close enough to inflict damage, destroying targets that conventional fire would have missed completely. The effectiveness was immediately apparent, with single shells destroying aircraft that previously would have required dozens or hundreds of rounds, with bomber formations being disrupted by defensive fire that had been ineffective before the proximity fuse's introduction. The Navy, which had sponsored the development program specifically to improve fleet anti-aircraft defense, began equipping all major warships with proximity-fused ammunition, transforming naval anti-aircraft capability from marginally effective to devastatingly lethal. By late 1943, Japanese pilots attacking American ships faced defensive fire that was fundamentally different from what they'd experienced earlier in the war. With shells that seemed to know where aircraft were and that detonated with uncanny accuracy, creating fields of shrapnel that aircraft couldn't evade through maneuvering. The psychological impact on attacking pilots was significant, knowing that American ships could destroy aircraft at ranges where previous defensive fire had been ineffective, knowing that tactics developed against conventional anti-aircraft fire were useless against proximity-fused shells that detonated automatically at optimal distances. The secrecy surrounding the fuses was maintained through careful operational security that prevented enemy forces from understanding what made American anti-aircraft fire so suddenly effective, with duds that failed to detonate being fitted with self-destruct mechanisms that ensured they wouldn't provide intelligence if they fell into enemy hands, with strict protocols requiring that proximity fuses be used only in circumstances where capture was unlikely. By mid-1944, proximity fuses had been adapted for use in artillery shells of all standard calibers used by American forces, extending the technology beyond anti-aircraft applications to create artillery ammunition that could be used against ground targets with devastating effectiveness. The adaptation required solving additional technical problems because artillery shells targeting ground forces experience different flight profiles and operational conditions than anti-aircraft rounds, requiring fuses that could distinguish between ground reflections and target reflections, requiring detonation heights that maximized anti-personnel effects rather than anti-aircraft effectiveness. The solution involved tuning the fuse sensitivity so that shells would detonate approximately 20 feet above the ground, creating airbursts that showered shrapnel downward over wide areas, penetrating foxholes and trenches and covered positions that provided protection against shells that detonated on contact with the ground. The tactical implications were profound, transforming artillery from a weapon that was most effective against exposed troops and equipment into a weapon that could kill soldiers in positions that conventional artillery fire couldn't reach effectively. The development of artillery proximity fuses was completed by late 1943, with production ramping up through 1944, but authorization for their use in Europe was withheld because of concerns that German forces would capture intact fuses and either copy the technology or develop countermeasures that would reduce effectiveness. The decision to withhold proximity fuses from ground combat in Europe while using them freely in the Pacific reflected military leadership's assessment that the Pacific theater's geography made capture less likely, with naval combat occurring over water, where duds sank out of reach, and with island fighting allowing better control over battlefields where unexploded ordnance might be recovered. In Europe, where ground combat occurred across territories that might be overrun, and where German technical capabilities were respected as potentially capable of reverse engineering captured examples, the risk seemed too great to justify the tactical advantages that proximity fuses would provide. The pressure to authorize proximity fuse use against ground targets in Europe came from multiple sources. As 1944 progressed and Allied forces advanced across France following the Normandy invasion, artillery commanders who'd heard about the fuse's effectiveness wanted them available for their batteries, recognizing that airbursts would be vastly more effective against German defensive positions than conventional fire. General Dwight Eisenhower, Supreme Allied Commander, received briefings about proximity fuse capabilities and understood the tactical advantages they would provide, particularly for breaking through fortified positions and for defending against counterattacks. The counter-argument from intelligence and security personnel emphasized the risk that German scientists could duplicate the technology if they obtained intact examples, potentially allowing development of proximity fuses for German anti-aircraft guns, defending industrial targets that Allied bombers were attacking, or worse, allowing development of countermeasures that would reduce the effectiveness of American proximity fuses that were protecting the fleet from Japanese kamikaze attacks. The debate continued through the summer and fall of 1944, with proximity-fused ammunition being stockpiled in European supply depots but remaining under strict employment restrictions that frustrated commanders who wanted access to the most effective artillery ammunition available. The compromise that emerged allowed proximity fuse use against V-1 flying bombs that were attacking England and later Antwerp, providing combat experience with the fuses in Europe, while minimizing capture risk because anti-aircraft fire occurred over friendly territory where recovery of duds was assured. The effectiveness against V-1s was spectacular, with anti-aircraft batteries equipped with proximity-fused ammunition destroying nearly two-thirds of flying bombs. They engaged compared to less than 10% with conventional fuses, validating the fuse's effectiveness and building pressure for their authorization against ground targets. The German offensive that began on December 16, 1944, changed the calculus about proximity fuse employment in ways that overrode security concerns and authorized their immediate use against the attacking forces. The Battle of the Bulge, as it would become known from the bulging salient that German forces created in Allied lines, represented Hitler's last major offensive gamble in the West, committing strategic reserves that Germany could barely afford in an attempt to split Allied armies, capture the critical port of Antwerp, and create conditions that might allow negotiation of a separate peace with Western allies that would free German forces to concentrate against the Soviet Union. The offensive achieved complete surprise, catching American forces in weakly held positions, pushing through initial defensive lines with armored spearheads that exploited the same terrain that had allowed German breakthrough in 1940. The weather was overcast and foggy, grounding Allied aircraft that might have interdicted German columns, giving attacking forces freedom of movement that allowed rapid advances that threatened to replicate the collapse that had defeated France 4 years earlier. American artillery became the primary weapon available to slow German advances, with batteries firing constantly to break up attacks, to disrupt German formations, to buy time for reinforcements to arrive and establish defensive positions that could contain the breakthrough. Colonel Axelson and other artillery commanders facing the German onslaught recognized that conventional artillery fire, while effective to a degree, couldn't deliver the devastating effect needed to stop attacks that were being pressed with desperate intensity by forces that understood this was their last opportunity to achieve strategic success. The authorization to use proximity fuses against German ground forces came from Eisenhower himself, within hours of the offensive beginning, overriding security restrictions that had kept the fuses from ground combat employment, because the tactical situation was so desperate that concerns about technology capture became secondary to stopping German advances that threatened to achieve breakthrough on a scale that could fundamentally alter the strategic situation in Europe. The decision was transmitted through artillery command channels with urgency that reflected the crisis conditions, with specific instructions that proximity-fused ammunition was to be used immediately and in maximum quantities against German forces, particularly against concentrations of infantry and against advancing columns where airburst effects would be most devastating. The shells that had been stockpiled in anticipation of eventual authorization were rushed forward to artillery batteries that were already engaged in continuous fire missions, with gunners receiving hasty briefings about employment procedures that differed from conventional ammunition. The proximity fuse, designated VT for variable time but called POSIT in field communications to maintain operational security, looked externally similar to conventional fuses, screwing into the nose of standard artillery shells, but the loading procedures were slightly different because the fuse had to be activated before firing by removing a safety pin that armed the electronics. Gunners who'd been firing conventional high-explosive shells with contact, fuses or time fuses that detonated on impact or after preset delays, now loaded shells that would detonate automatically when the fuse sensed proximity to the ground, creating airbursts that would shower shrapnel downward over areas much larger than contact-detonated shells could affect. The first proximity-fused artillery fire missions during the Battle of the Bulge were fired on December 17th, the second day of the German offensive, with batteries that had been firing continuously since the attack began now switching to ammunition that would prove devastatingly more effective than what they'd been using. The psychological impact on American gunners was immediate and positive, with crews understanding they were finally being allowed to use ammunition they'd heard about but had been forbidden to employ. Ammunition that promised to transform their effectiveness against enemy forces that were threatening to overrun defensive positions. The effect of proximity-fused artillery fire on German forces attacking through the Ardennes was catastrophic in ways that transformed the tactical situation and contributed significantly to the ultimate failure of the German offensive. German infantry who'd been trained to take cover in foxholes and depressions when American artillery fire began now discovered that the positions that had previously provided protection were death traps when shells detonated 20 feet overhead, showering shrapnel straight down into holes that offered no protection from above. The psychological impact was immediate and profound, with German soldiers reporting in interrogations after their capture that American artillery had become impossibly deadly, that positions that should have been safe were no longer protecting them, that the only warning before shells detonated overhead was the whistle of incoming fire that didn't give time to react. One captured German soldier described the attacks as quick, powerful bursts that seemed to seek out covered positions, that exploded with timing that suggested the shells somehow knew where troops were hiding. That created terror, unlike anything he'd experienced in 2 years of fighting on the Eastern Front, where Soviet artillery was notorious for its volume, if not its accuracy. The casualties from proximity-fused fire were significantly higher than from conventional artillery, with medical personnel treating wounds that showed shrapnel had come from above, rather than from the side or from ground-level fragmentation that contact fuses produced. German unit commanders began reporting that their forces couldn't advance under American artillery fire, that casualties were mounting at rates that made offensive operations unsustainable, that the artillery fire they were experiencing was fundamentally different from what they'd encountered earlier in the war. The after-action reports compiled by German divisions during and after the battle repeatedly mentioned the devastating effectiveness of American artillery, with specific comments about airbursts that seemed to target troops in covered positions, though without understanding of the technology that made this possible. The fear that proximity-fused artillery created spread through German units faster than official reports could travel, with soldiers telling each other that American shells had new fuses that made foxholes useless, that the only safety was in heavily reinforced bunkers or buildings that could provide overhead protection, that attacking across open ground under American artillery fire was suicide, because the shells would kill you whether you were standing or prone or in a hole. The tactical employment of proximity-fused artillery during the Battle of the Bulge followed patterns that artillery commanders developed through experience during the first days of the offensive. Learning how to maximize the devastating effects that airbursts produced, forward observers directing fire missions discovered that proximity-fused shells were most effective against troops in the open or in field fortifications, with single volleys producing casualties that would have required sustained fire missions using conventional ammunition. The standard procedure that emerged involved using proximity fuses for all fire missions against personnel targets, concentrating fire on areas where German forces were forming up for attacks, where columns were moving through forests or along roads, where defensive positions were being established. The effectiveness was dramatically higher than conventional fire, with forward observers reporting that German forces caught in proximity-fused barrages suffered casualties that forced them to withdraw or abandon attack plans. That column struck by airburst fire lost cohesion and combat effectiveness, even when overall casualties weren't overwhelming, because the psychological impact demoralized survivors. Artillery officers learned to time their fire missions to catch German forces at moments of maximum vulnerability, waiting until attacks were committed and then bringing down proximity-fused fire that disrupted formations and broke momentum that was essential for offensive operations. The coordination between forward observers and firing batteries reached levels of efficiency that reflected both the desperation of the tactical situation and the recognition that proximity-fused ammunition was a battle-winning weapon that needed to be employed with maximum effectiveness. Batteries that had been firing 10 to 20 rounds per mission with conventional ammunition now fired similar numbers with proximity fuses, but achieved results that previously would have required hundreds of rounds, allowing artillery groups to engage more targets with the same ammunition expenditure, or to achieve overwhelming effects by concentrating fire that would have been wasteful with conventional fuses. The ammunition expenditure during the Battle of the Bulge was enormous, despite the increased effectiveness per shell, with batteries firing thousands of rounds daily, as the intensity of combat demanded continuous artillery support for defensive positions that were under constant German pressure. The supply system that delivered proximity-fused shells to forward artillery positions operated under extreme conditions, with convoys navigating roads that were threatened by German penetrations, with supply officers prioritizing proximity-fused ammunition over other critical supplies, because artillery commanders were demanding more rounds than logistics could sustainably provide. The production capacity that had been developed during 1943 and 1944 proved barely adequate for the demand that the Battle of the Bulge created, with factories in the United States working around the clock to produce fuses that were being shipped across the Atlantic and rushed forward to artillery units that were consuming them faster than planners had anticipated. By the end of December, after 2 weeks of intensive combat, American artillery had fired approximately 200,000 proximity-fused shells, according to post-war assessments, a staggering quantity that indicated both the scale of the battle and the importance that commanders placed on using this ammunition. The effectiveness was reflected not just in casualties inflicted, but in the collapse of German offensive capability, with attacks that had pushed forward aggressively, during the first days of the battle becoming tentative, and then stopping entirely as German forces lost the ability to concentrate for assaults without suffering prohibitive casualties from American artillery fire. General George Patton, whose Third Army counterattacked from the south and played a crucial role in containing and then reducing the German salient, credited proximity fuses with being second only to the atom bomb in winning the war, a hyperbolic statement that nonetheless reflected the tactical significance that commanders attributed to this technology. The German response to proximity-fused artillery was hampered by their inability to understand what was making American artillery fire so suddenly devastating, with field commanders reporting that American shells seemed to be exploding in the air above their positions, but without clear understanding of how this was being achieved or what countermeasures might be effective. German intelligence efforts to recover intact proximity fuses for examination were complicated by the self-destruct mechanisms that were built into the fuses, with unexploded rounds destroying themselves when disturbed, or when the battery that powered the fuse electronics expired after several minutes, preventing recovery of examples that could be examined by German scientists. The few intact fuses that were recovered and sent to technical intelligence units arrived too late in the war to allow meaningful reverse engineering, with German research programs having been disrupted by Allied bombing and by resource shortages that made development of complex electronics increasingly difficult. Interrogations of Hermann. Göring, after Germany's surrender, revealed that German intelligence had suspected the existence of proximity fuses based on the effectiveness of Allied anti-aircraft fire against V-1 flying bombs, and that German scientists had been working on their own proximity fuse development programs since 1941, but that Hitler had personally ordered these programs halted in 1942 because he believed the war would be won before such long-term research projects could produce results. A decision that proved catastrophically wrong when American proximity fuses began devastating German forces during the Battle of the Bulge. The German Technical Intelligence Services had identified more than 30 different proximity fuse designs in various stages of development or production by Allied forces, demonstrating that German understanding of the technology existed, but the inability to obtain intact examples for detailed examination and the resource constraints that limited German electronics production meant that countermeasures were never developed and German forces had no effective response beyond trying to avoid concentrations that would attract American artillery fire. The tactical adjustments that German forces attempted in response to proximity-fused artillery fire proved largely ineffective because the fundamental problem wasn't solvable through tactical changes, but rather reflected a technological and material advantage that Germany couldn't counter. German units began dispersing more widely to reduce casualties from individual artillery strikes, but dispersion reduced the concentration necessary for effective attacks and made command and control more difficult in the confused conditions of the Ardennes fighting. German commanders tried to move forces during periods of limited visibility when American forward observers couldn't direct fire effectively, but proximity-fused ammunition was equally effective in time-fire missions, where forward observers weren't adjusting individual rounds, with battery commanders calculating coordinates and firing volleys that covered areas where German forces were suspected to be concentrating. The attempt to use heavily forested areas for cover proved ineffective because proximity fuses detonated above the tree canopy, with shrapnel-penetrating foliage that would have provided some protection against ground-burst fire, and because trees struck by shrapnel created secondary fragments of wood and branches that added to casualties. German forces discovered that the only truly effective protection against proximity-fused fire was substantial overhead cover, either in reinforced bunkers or in buildings with thick roofs, But such protection was rarely available in the forest and rural areas where most of the Ardennes fighting occurred, and troops couldn't remain in protected positions indefinitely when offensive operations required movement and exposure. The cumulative effect of these failed countermeasures was that German forces learned to fear American artillery in ways that affected combat effectiveness beyond the physical casualties inflicted, with soldiers becoming reluctant to move when artillery fire was falling, with attacks losing momentum as troops sought cover rather than pressing forward, with the offensive spirit that had characterized the initial German assaults dissipating as casualties mounted and the prospect of success diminished. The weather that had initially favored German operations by grounding Allied aircraft cleared on December 23rd, allowing American air power to join the battle and further tilting the balance against German forces who now faced both devastating artillery fire and air, attacks that disrupted rear areas and destroyed supply columns. The combination of proximity-fused artillery and air superiority created conditions that made continued German offensive operations impossible, with forces that were already suffering unsustainable casualties from artillery now being attacked from the air as well, with supply lines being interdicted and reinforcements being destroyed before reaching forward units. The German offensive, which had achieved surprise and initial success through favorable weather conditions and the weakness of American defensive positions, was now confronting the full weight of American material superiority applied through technologies and capabilities that German forces couldn't match. The proximity fuse was one component of this material advantage, but it was the component that had the most immediate and devastating effect on German infantry, who bore the brunt of the fighting, who experienced firsthand the terror of artillery fire that made traditional defensive measures useless, who learned through costly experience that American technological and industrial advantages had produced weapons that transformed tactical equations in ways that German training and tactical skill couldn't overcome. The strategic implications of proximity fuse employment during the Battle of the Bulge extended beyond the immediate tactical effects to influence Allied planning for subsequent operations and German understanding of their strategic situation. American commanders who'd been skeptical about the tactical value of proximity fuses or who doubted whether the technology justified the security risks became convinced advocates after witnessing the devastating effectiveness during the Ardennes fighting. The restrictions on proximity fuse employment that had characterized operations through 1944 were completely lifted after the Battle of the Bulge, with proximity-fused ammunition becoming standard for American artillery operations throughout the remainder of the war in Europe. The production priorities that had constrained proximity fuse availability were revised to increase output, with factories that had been producing conventional fuses being converted to proximity fuse production, with quality control procedures being streamlined to increase manufacturing rates without compromising reliability. The psychological impact on German forces extended beyond those who directly experienced proximity-fused fire to affect German military morale generally, with soldiers throughout the Wehrmacht learning that American artillery had become impossibly deadly, that defensive positions that should have provided protection were no longer safe, that the material advantages American forces enjoyed included technologies that transformed basic tactical situations. The recognition that Germany couldn't counter or match American technological advantages contributed to the collapse of German military morale during the final months of the war, with soldiers increasingly convinced that continued fighting was pointless when facing enemies who possessed such overwhelming material and technological superiority. The post-war assessment of proximity fuse effectiveness during the Battle of the Bulge confirmed what field commanders had reported during the fighting, that this technology had been decisive in stopping the German offensive and in inflicting casualties that degraded German combat effectiveness to levels that made continued operations impossible. American casualties during the Battle of the Bulge were significant, with approximately 80,000 American soldiers killed, wounded or captured during the 6-week battle, but German casualties were higher despite their initial advantages of surprise and momentum, with estimates suggesting over 100,000 German casualties, including prisoners. The casualty ratios in artillery exchanges favored American forces by margins that were unprecedented in conventional combat, with proximity-fused fire inflicting casualties at rates 5 to 10 times higher than conventional artillery, according to some post-war analyses. The effectiveness wasn't just measured in casualties, but in the operational impact, with German units losing combat capability due to morale collapse and disruption that exceeded what physical casualties alone would have produced. The veterans who survived the battle on both sides carried memories of proximity-fused artillery that shaped their understanding of modern warfare, with American soldiers remembering the psychological boost of knowing they possessed weapons that were decisively superior to enemy capabilities, with German soldiers remembering the terror of artillery fire that seemed impossible to survive, and that made fighting pointless. The technological advantage that proximity fuses represented became emblematic of the broader material superiority that determined the war's outcome, demonstrating that industrial capacity and technological innovation could produce weapons that transformed tactical situations in ways that training or courage or tactical skill couldn't overcome. The meeting that occurred in 1978 between a former American artillery officer who'd commanded a battery during the Battle of the Bulge and a former German infantry officer who'd survived the battle captured something essential about how veterans from opposing sides understood the role that technology played in determining outcomes. The American officer, by then in his 60s and retired from a post-war army career, was attending a military history conference when he encountered the German veteran who introduced himself as having commanded a company during the Ardennes offensive. The German officer had been wounded by artillery fire on December 20th, had spent 2 weeks recovering before returning to his unit, which by then had been withdrawn from combat after suffering casualties that reduced it below effective strength. He'd heard stories about American proximity fuses after the war and wanted to understand from someone who'd used them what the experience had been like from the American side. The American officer described the authorization to use proximity fuses coming as the battle began. The hasty training on employment procedures, the immediate recognition that the ammunition was devastatingly more effective than conventional fire, the satisfaction of finally being able to use technology they'd known existed, but had been forbidden to employ. The German officer listened and then described what proximity-fused fire had been like from the receiving end, the terror of shells that detonated overhead without warning, the realization that foxholes provided no protection, the breakdown of unit cohesion as soldiers became reluctant to move under artillery fire, the sense that American forces possessed technologies that made German resistance futile. He asked whether American forces had understood during the battle how completely their technological advantages were determining the outcome, whether the men firing the guns had recognized they were using weapons that were fundamentally changing the tactical balance. The American officer responded that individual soldiers rarely thought in those terms during combat, that gunners were focused on serving their weapons and completing fire missions, that the broader implications of technological superiority weren't apparent until after the battle, when casualty reports and operational analyses revealed just how decisive proximity fuses had been. They talked for nearly an hour about the relationship between technology and combat outcomes, about how material advantages shaped tactical possibilities, about whether wars could be won by better equipment or whether human factors remained determinative. The German officer expressed a view that stayed with the American for years afterward, that perhaps the Battle of the Bulge had been Germany's last moment when tactical excellence and soldier quality might have overcome material disadvantages, and that proximity fuses represented the technology that definitively proved that material superiority had become determinative in modern warfare. When they parted, both men acknowledged that the conversation couldn't change what had happened or make the losses any less tragic, but that understanding how former enemies experienced the same battles from different perspectives helped make sense of experiences that had been defining moments in their lives. The legacy of proximity fuse employment during the Battle of the Bulge influenced military technology development throughout the remainder of the 20th century and into the modern era, establishing principles about the relationship between technology and tactical effectiveness that shaped how militaries approached weapons development and procurement. The recognition that a relatively small technological advantage in a critical weapon system could produce disproportionate tactical effects influenced Cold War military planning, with both American and Soviet forces investing heavily in technologies that promised similar advantages. The development of guided munitions, precision weapons, advanced sensors, and network-centric warfare capabilities all reflected lessons learned from proximity, fuse effectiveness about how technology could transform tactical situations. The proximity fuse itself continued to evolve, with post-war developments producing more sophisticated versions that could discriminate between different target types, that could function in electronic warfare environments, that could be integrated with guided weapons to increase effectiveness. The basic principle that proximity fuses demonstrated that weapons which could sense their environment and adjust their behavior accordingly were vastly more effective than weapons that operated according to preset parameters became foundational to modern military technology development, influencing everything from air-to-air missiles to anti-ship weapons to terminal guidance systems for artillery and bombs. The story of proximity fuses at the Battle of the Bulge became part of military education, taught to officers learning about the role of technology in warfare. Used as an example of how scientific research and industrial capacity could produce weapons that transformed tactical possibilities. The veterans who'd experienced proximity-fused fire from either side became part of the historical record, their testimonies and after-action reports providing evidence for effectiveness that shaped understanding of how this technology had contributed to Allied victory. The proximity fuse mattered not just because it killed German soldiers more effectively than conventional weapons, but because it represented the application of American scientific and industrial capabilities to military problems in ways that enemies couldn't match, demonstrating that the outcome of modern wars would be determined as much by technological innovation and production capacity as by traditional military virtues of courage and tactical skill, establishing patterns that would characterize warfare throughout the remainder of the century and beyond.